And can we go to Taylor for 1?
This section will review the technique imported graphs, a couple of formulas, formula.
Raise your hand if you think you might know the distance formula. It's got a big old square root in it. Hands if you think you know the distance formula. Okay. Hands if you think you know the midpoint formula. Hands if you've at least seen either of these things. Okay. All right, let's go to the other Taylor for 2. Okay, can you guys do this and work closely with your neighbors? First observation, what do you get when you graph these 2 things? What's the name of the thing? Is that a parabola that you drew? It is linear, it is a line, right? When you graph one of these things, you draw a line. That's why we call it a linear equation. So the first one, you can pick your favorite number for x and then figure out what y is, or the other way. You can pick your favorite number for y and figure out what x is. For an equation that looks like this, with the x's and y's all mixed up, I think the easiest numbers to plug in are 0 for each of them separately. So if you plug in x equals 0, and I like to do this by just kind of covering up. If x is 0, then this first term is nothing. So how much is y? 6, and it's just staring at you in the face, right? And so you get the point 0 and 6. And so I like doing that because it's so easy to just cover something up. Same idea. If you plug in y equals 0, then the second term isn't there, so we cover it up. Okay, you have a little bit of work to do. How much is x? 3. And then we have our second point. 3, 0. And then we plot those 2 points. Those 2 points have a special name because they're on the axes. Those are the intercepts. Good. Intercepts. X-intercept is on the x-axis. Y-intercept is on the y-axis. And then you just connect the dots with a straight line. Hey, that was pretty good. Nice thing about recording it is later on I could check it out. Just put it on my greatest hits reel. Don't worry about the curve in the line at the bottom. Okay, so that's that. Did everybody pick those exact points? Everybody did? I saw some folks had different points. Some of you guys had like 2 and 2. Yep. Did everybody get the same line regardless of which points we picked? Yes, that's the idea. Joe. All right, so Joe connected the points and stopped, yes? Okay, is this right? Yeah, the line continues, right? And so like Joe is not an arrogant person, but it's arrogant to say the line exists only between these points that I pick, right? Right, the line goes forever. The line doesn't care about Joe's points. So you're just finding any 2 points and then connecting them. So it does go forever. I'm glad you mentioned that because this is real common to just draw the line segment, but it goes forever. Arrows would be great to indicate if you want, but I don't need to see them. And then the same idea for part B, but part B is a little bit different because here X and Y aren't together on the same side. Y is by itself. And if you see that, then it turns out it's actually quite a bit easier to pick 2 different values of X and find the values of Y. For example, if I were to plug in 5 here for Y, is that arithmetic or is that algebra to solve that? That's algebra, right? It's not hard algebra, but it's algebra. But going the other direction, if I were to pick, say, 2 for X, and I plug in a 2 right there, is that arithmetic or is that algebra? That's arithmetic, which is a lot easier. So you pick your favorite X, and then you pick your X favorite X, and you find the Y values. So for me, what do I get here? I get 5, and -2 plugged in gives me -7. So I can pick these 2 points, connect the dots. So we go 2, 5, and we go -2, -7, and I, nope, missed that one. -2, -7, and then we connect the dots with a straight line, and that's it. And even if you pick different points, you should all have that line going uphill pretty steep. Any questions on that? Okay, we'll go to the bottom here, this note. I think we're back to Tyler. Okay, so that's an important observation. I didn't label it, but let's label this point right here. What are the coordinates? 3 and 0, and that is the x-intercept. So if you're thinking about an x-intercept, you know that y is definitely 0. It doesn't matter what line we're talking about. If you're on the x-axis, how much is y? It's 0. And then the other way for the y-intercept. Katrina for 3? Okay, so it's a big idea, which means we pause here before we turn the page. Take a look at this point right here. What does it look like the coordinates of that point are? That looks like a 1 and a 2. Now, it's not necessarily perfect. This was a freehand thing, but it looks pretty close to being like right on the point 1, 2. So what are we saying? We're saying that if x is 1, then y is 2, but that's somehow supposed to have something to do with this equation. If you plug in x equals 1, so this is a 3 times 1 minus 1, right? Plugging in x equals 1. And if I plug in what value for y at that point? 2. Is that equation true or is it false? It's true. And that's the idea. That's what the line is. When you draw a line, you're not just drawing this random thing connecting two dots. You're finding a whole bunch of points, infinitely many points, that if you plug them into the equation, it makes the equation true. Didn't need to be true, but it was true because you picked a point that was on the line. This point 1, 2 is on the line. Therefore, 1 and 2 satisfy the equation. And the other direction is true as well. If you have a point that satisfies the equation, where's it going to be? It's going to be on the line. If you have a point that satisfies the equation, it will be represented somewhere on that line. And if you decide to just do something crazy like out here, I picked this point. What are the coordinates? 8 and 1. Can you guys plug in 8 and 1 into that equation? So y equals 3x minus 1. How much is the y at this point? 1 equals 3 times how much is x? 8 minus 1. Is it true? No, of course it's not true. Why isn't it true? The point 8, 1, not on the line, right? If you're on the line, you make the equation true. If you're not on the line, the equation isn't going to be true. So that line is all the points that make the equation true. And like, I feel like I'm saying things that, you know, it's like, oh, of course, well, yeah, that's all true, right? That's sure. But I think it's an important connection to have. The points on the line have an awful lot to do with that equation. And the equation has an awful lot to do with the line. And it's a good connection to make. When you're ready, we'll go to the next page. And we're up to Serge for number 4. Okay, so there is a distance formula. I'm not going to use it right now, but I'll show it to you in just a minute. But what I am going to do is I'm going to draw this guy right here straight down until we get here, and then I'm drawing straight to the right. Now, what kind of a special triangle is that? That's a right triangle. Now, can you figure out how tall this right triangle is? How tall is that? That's 6. Can you figure out how long or how wide it is on the bottom? Is that 8? And that little symbol there means what? It means a right angle, a 90-degree angle. Do you guys know the most famous theorem in all of math? Is the Pythagorean theorem. There are a lot of theorems in math. We're going to see a bunch of them this semester. But the most famous theorem in math is the Pythagorean theorem, which says that if you have a right triangle and you call this guy A and this guy B and this guy C, then what magical equation is true? This is something we've seen before, right? Okay, so I can plug into my equation. How much is A in this triangle? 6. So this is a 6 squared plus, how much is B in my triangle? 8. That's 8 squared equals C squared. But C is the thing I'm trying to find. It's how long is that line segment? And we just have to churn through. 36, 64, C squared, 100, C squared. So C is the square root of 100. Most square roots are not nice, but this one happens to be How much is it? 10. So the length of that line segment in pink is 10. Questions on that one? And maybe some of you guys have memorized some Pythagorean triangles, like a 3, 4, and 5. So Connor's heard of the 3, 4, 5 right triangle. Well, this one is just double those numbers. 3, 4, and 5 doubled becomes 6, 8, and 10. Okay, so but there's a formula happening in here. So let's see if we can pull apart the formula. What are the coordinates of this point right here? This point at the top? -3 and 3. And Eliza's already pulling out the formula here. What's the other point? -5 and -3. So if we know those coordinates right there, do you see how we got that it was 6 tall? Like you got 6 by counting boxes, right? I want to do this without counting boxes. I want to just look at those coordinates. Why is it 6 tall? Why? So you're looking at the -3 and the 5 for this one?
Oh, wait, no.
Yeah. Why is it 6 tall? Well, the tall is the y value, right? How high and how low it is the y value. So the top point was 3 high. The bottom point was 3 below. So altogether, that's a change of 6, right? And if you're thinking about just doing operations on these numbers without having a picture in front of you, if you do 3 minus -3, what do you get? You get 6. That's why it's a 6. It's the top number minus the bottom number. 3 minus -3. And go in the same direction, but now we'll think about this guy. Why is it an 8? Well, how much was it here? It's 5. And the other one, -3. How do we get 8 out of those? 5 minus -3. You subtract them. And so there's this nice kind of symmetry happening here. You subtract the y's, that tells you how tall it is. You subtract the x's, that tells you how long it is horizontally. And once you know those things, Pythagorean theorem takes you the rest of the way. Okay, so the good news is people have done this in general. Let's take a look at 5. We'll go to, I completely lost it. What's your name again? Joe, number 5, please. Okay, same idea. You got these points, x2 and y2, x1 and y1. The numbers, those little subscripts, they don't have anything to do with the values of the x coordinates or the y coordinates. They're just our way of saying the point with the 2's is our second point, and the point with the 1's is our first point. But don't worry about the subscripts. So how do you find how tall it is? Well, you subtract which ones to find how tall it is? You subtract the y's. So you do y2 minus y1, that's there. That's how tall the triangle is, that's this. And how do you find how wide it is? You subtract the x's, x2 minus x1. What are the funny symbols? What is this? Absolute value. That's just our way of making sure you get positive numbers. So just, you would subtract in the right order if you had the picture, but if we just want a formula and we don't care about the order, just make sure it's positive when you're done. And then according to Pythagorean theorem, let's see, so it was the a squared. So a was this vertical distance. So we're supposed to take the vertical distance, which is this y2 minus y1, and we're supposed to square it, right? That's Pythagorean theorem, plus the horizontal distance, x2 minus x1, and that's squared. That's my a squared plus my b squared. And that's supposed to equal the c squared, right? But how about we solve for, what's that, Eliza? Yeah, so maybe we'll call it d for distance instead of c. But let's solve this equation for d. What do you do to both sides? Square root it. So I will get rid of that guy. I'll put a big old square root. Technically plus or minus, but it's a distance, so plus. And that's the formula that maybe some of you guys have seen before, maybe some of you still remember. That's the distance formula. Okay, and the formula down below, you can see it here. Is it the same? It just had the x's first, but it doesn't make any difference, right? So I'll tell you, when I was learning this distance formula as a student myself, I could never remember. I knew there were pluses and minuses in here, but I could never remember which ones were which. I knew that, you know, like either this was minus and the middle was a plus. That's the right answer. Or I knew that like this was a plus and this was a plus and this was a minus, and that's the wrong answer. And so honestly, I got some of these wrong just because I couldn't remember where the pluses went and where the minuses went. But I didn't realize it was Pythagorean theorem. Pythagorean theorem has what in it? It's plus. A squared plus b squared. I knew that. Well, it's Pythagorean theorem. Stick a big plus right in the middle. That's what's getting squared. Two things squared, plus in the middle. The other ones are subtract. Okay, so that distance is there. And then I have this nice little visual here we'll just take a quick look at. Have we looked at this program before? I don't think we have. This is a program called Geometers Sketchpad, and it's a nifty little thing. So here's the start. You guys, we had these points before, right? The -3, 3, and the 5, -3. Those are the points that we had. Okay, so we want the vertical and horizontal parts. So that's that, and then so those are drawn in, and then the vertical distance. So click that one, and that distance was 6, right? How long was the horizontal? Was it 8? That's the 8. And then you want to find the distance. That's the Pythagorean theorem that we saw before. So we get 10. And I think this will work. I think if I just grab this thing, then what happens? What happens to all the numbers? They just update. But it's always the same. Pythagorean theorem is always the same. Subtract, subtract, square, add. So the formula always works. This is just kind of a nice visual that it automatically updates. And that's it. So let's try number 6. 6, we're up to Ben. Okay, can you guys try that using the formula without plotting the points? Just use the formula to find that distance and check with your neighbors. Okay, did we get the square root of 41? Did anybody get 9 as the answer? Yeah. So so let me tell you how you can get 9 as the answer. If you look at this square root of 16 plus 25, and you decide, oh, okay, I can split that up. Square root of 16 plus square root of 25, right? Just splitting it up. How much is the square root of 16? 4 plus 5 is 9. Is that right? No. Square root of 41 is definitely right. I mean, you plug it into the formula, and that's what you get. So where did we go wrong? You can't split a square root like that. You can't. Square roots work real good with multiplications and additions. Sorry, multiplications and divisions. You can't split up a square root over a plus. You want to see the proof? There it is. 9 is not the square root of 41. It just doesn't work. So don't do that. Square root of 41 is it. If you want a decimal, you type it into the calculator. What is it, like 6.4? Great. That's how far apart those points are. All right, how about we try 7, and I think we'll go to Sam. Okay, thank you. Eliza? The midpoint formula. Okay, so it's a different formula. I'd like to appeal to your sense of geometry again on this one. So let's come back to this guy right here. Okay, I'm trying to find the middle of this line. So let's see, I don't know that I can write on this. Can I write? No, I can't write on this. But the middle of this line, let's see, so coming in someplace around there-ish, we buy it, like it's somewhere in there, around the middle of the line. So tell me if you believe this. The middle of the line, which is this guy right here, I can think of it as maybe separating the x's and the y's out. Look at the x's. The x's are -3 and 5. Do you believe that if I find the middle of those numbers, so 5 is over here, -3 is over here. Do you believe if I find the middle of those two numbers right there, that I'm going to find the middle of this line? I've got 5 is out here. We've got -3 is out here. If I find the middle of, whoopsies, I don't have like an undo button here. It's okay. But if I find the middle of the line, the middle of the x's, then that's going to find me the middle of the line. So let's give it a shot. Here's the vertical midpoint. Wait, lost some stuff somehow. Okay, so there's the same right triangle that we drew before. I'm going to find the middle of the vertical and the middle of the horizontal. Middle of the vertical is right there, green. Middle of the horizontal is right there. Do you guys see how we're going to get from those two green points to the answer? Can we, yeah, like kind of see like we're going to, here, this is my favorite part. You ready? Yeah, is that cool? I'll do it again because we didn't get the response we were supposed to. That's still fairly lame on your part. Here, one last time. Oh, yeah. I know, right? Yeah, so you find the middles of the vertical and the middle of the horizontal, and you just shoot over to the midpoint. So how do you find the middle? How do you find the number that's right in the middle of two other numbers? What do we call that in math? You got two numbers and you want to find the number in the middle. That's the average, yes? So how do you find the average of two numbers? What do you do with them? Add them and divide by 2, right? If you have two numbers. You want to find the average of two numbers, you add them and divide by 2. Well, guess what the midpoint formula is? Add the two x's and divide by 2. That's the right answer for the x. Add the two y's and divide by 2. It's just saying average the x's, average the y's. So how are you supposed to keep all these formulas straight? Well, I'm hoping that you're getting some intuition about why these formulas are true. It's not just random. Like when I learned it, it was like, shoot, are those pluses or minuses in the distance formula? I don't remember. It's because I didn't understand what I was doing. But if you know it's Pythagorean theorem, that's a plus in the middle of the Pythagorean theorem. In the midpoint formula, it's really easy to put subtraction instead of addition. And in fact, real soon, I don't know, we've talked about slope, right? Have we talked? No, we haven't talked about slope. We will talk about slope. But what's the formula for the slope? Rise over run is good. I'll write a formula that, we'll see this later on, but maybe you've seen this formula before? Have we seen that? y2 minus y1 over x2 minus x1. Well, I mean, it's really, really easy to start losing track of the pluses and minuses. I see x's and y's like added together. Here, I see x's and y's subtracted. I mean, they're not that different. So you got to keep them straight. Now, I know on the quizzes, you can have a reference card, right? Well, index card. You can write all these formulas down, and I think you should. And the same thing on a test. But if you don't have the formula in front of you, just think about stuff. Middle, average. How do you average? You add the numbers and divide by 2. Let's try the next page, number 8. Who is our reader for number 8? Is it Megan? Okay, can you guys use the formula that we just talked about to find the midpoint of that line segment? All right, did we get 1, 0? Any questions on this one? Any questions on the midpoint? Okay, I'm going to try to challenge you a little bit. Instead of just plugging into a formula, we're going to ask you to think about some stuff. Suppose that that line segment right there was extended. And it went this way and a little bit off the screen. And suppose that I tell you that this point right here is the midpoint of the new thing, which goes a little bit off the screen. You understand? What am I going to ask you to, so this is a line segment, it's a little bit bigger than is on the screen, and I'm telling you that -3, 3 is the midpoint. What am I going to ask you to find? The other point. And you guys work with your neighbors. See if you can find the coordinates of this other point to make it so that that negative 3, 3 is the midpoint of the new bigger line segment. Over here? No, I think it's positive 1. You have negative 3 plus 5, right? Yeah. Let's think about this tougher question here. I saw actually a couple of different techniques, both legitimate for this problem. Suppose that we call the coordinates, suppose that we call the coordinates of this unknown point out here. Let's just call it like x and y, to be determined, this thing off the screen. So here's something that I know. I know that if I do the midpoint stuff, I'm supposed to average the ends of my line, right? One endpoint, the other endpoint. So I'm supposed to average the x and the 5, which means you can do x plus 5 over 2. That's averaging the x's. And then separately, I can average the y's, some unknown y and the number negative 3 added together. Y plus negative 3. Always divide by 2 for the midpoint formula. Okay, that right there is the midpoint of 5, negative 3, and some arbitrary x, y out here. But I know what the midpoint is supposed to be. What is the midpoint supposed to be in this problem? This negative 3, 3. That's what I'm after. So what do? You set it equal to negative 3 and 3. You make the midpoint, set it equal to the right answer, and then you got to do a little bit of work to figure out what x and y are. So the work is actually not so bad from here, but are there questions on that setup? Yeah, that's the idea. Make the yellow things equal to each other and separately make the green things equal to each other. And if you do that, ultimately you end up with, what's the answer? Negative 11 and 9. So I'll put like a dot, dot, dot in between here. There's some work that we're not going into the details of. Super, this is the algebra way to do this. There's also a really nice geometry way that I think is even easier than that if you've got a picture in front of you. And that's to try doing something like this. Suppose that you start at this point at the bottom right, and you decide you're going to walk your way to the middle. How far up do you need to walk? 6 up, and then how far to the left do you need to walk? Is 8 to the left. Up 6, 8 to the left. Do you buy it that if I want to land on the right point out here, I should make that same walk again? Because I'm in the middle. So to get from the end to the middle is the same trip as getting from the middle to the other end. So if you go up 6 and left 8, you'll get the answer. So how am I supposed to do that? Well, up 6 used to be 3. Go up 6, where do you land? You land on 9. Exactly the 9 in the answer. Used to be negative 3. I'm trying to go 8 to the left. It's negative 11. It's a really nice way to appeal to the geometry in the picture. Okay, let's take a look at number 9. Number 9, we are up to Connor. Okay, so let's take a look at this picture. I'll start with the y-intercepts. So I've got this graph. It is more complicated than anything I'm expecting us to be able to just generate, but I would like us to read some information off the picture if I give you the picture. Okay, so let's look at the y-axis. How many times does the curve hit the y-axis? Just once. Right there. What are the coordinates of that point? 0, 0. So the y-intercept, 0, 0. It's the only place where the curve hits the y-axis. How many times does the curve hit the x-axis? 3 times. One there. I'm going to have a hard time here. I'm going to put it above, but it's really the same point. And then the last one is out here. So list the coordinates of the 3 x-intercepts. So what are they? Good. So this graph has 3 x-intercepts and 1 y-intercept. It happens that the y-intercept is an x-intercept as well. And just kind of another defining characteristic. What's the common theme for all the green points? Looking at the numbers. Eliza? The y is equal to 0. Everybody see it? For all the x-intercepts, which are green, the y is equal to 0. And we read that earlier today. Yes? Let's see. So Eliza's seeing the 3 in the x cubed and finding that there's 1, 2, and 3 x-intercepts. Do we see what she's looking at? So the question is it a coincidence? It's a really good question. Have I mentioned in this class the fundamental theorem of algebra? Nice and loud. Yeah. So this thing that Eliza is seeing as a, like, is it a coincidence? No, it's not a coincidence. And in fact, it's this theorem called the fundamental theorem of algebra. How many fundamental theorems of algebra do you think there are? 1. The fundamental theorem of algebra says exactly what Eliza has recognized and what Taylor has seen before, is that the number of x-intercepts, the number of places where the equation is true, is exactly the same as the highest power. Have we brought this guy out in this class before? Yeah. Who got the thinker before? I forget. Sam. Yeah. Okay, so Eliza, for recognizing that pattern. Okay, let's see if we can continue Eliza's observation here. Here's an equation. X squared minus 5x plus 6 equals y. How many x-intercepts are you expecting to see according to Eliza's observation? We're expecting to see 2. So let's see if we can't find them. X and y-intercepts both. Okay, the y-intercepts are always easier than the x. We'll start there. What's true if you are sitting on a y-intercept? Yeah, we know that x is equal to 0. If you are at a y-intercept, x is equal to 0. Great, let's use the equation. Y equals 0 squared minus 5 times 0 plus 6. And we get 6. To find the y-intercept, you plug 0 in for x. It's always easy. In theory, I should take off points if you just say 6. What are the coordinates of the y-intercept? 6 and 0? 0 and 6? Which one is it? 0 because x was 0, and then the y is 6. That is the y-intercept. I said in theory I should take points off if we just say 6. Now I don't generally try to go out of my way to be mean. I will take points off if you just say 6, but I'm going to do my best to make sure that I ask the question as follows. Give both coordinates of the y-intercept. That make sense? I'm not saying there's 2 points. I'm saying there's 1 point with 2 numbers in it. Give both coordinates of the y-intercept. I'm going to really try to use that language to remind you that y-intercept has 2 numbers. First one's always 0. Okay, let's answer the tougher question. The x-intercept. What do we know is true? We know that y is equal to 0. Great. So we're going to write the same equation, but instead of y, what are we putting? 0. We go 0 equals x squared minus 5x plus 6. And at this point, we could go to Wolfram alpha. Let's roll up our sleeves and factor instead, just to get some practice. Factor that equation and find x. Okay, any luck factoring this thing? What do we get? Okay, I trust that you guys have a lot of practice with that. If you don't have enough, I'll tell you where you can find more, but you got to practice with that. And then we split it up. So how much is x? 3 or 2. And if we want full credit, These are points. 3, 0, 2, 0. And as Eliza goes to her appointment, how many answers did we get to the equation? We found 2, as she predicted. Yes. Yeah, this you'll see 150 on the video. You're welcome. Okay, any questions on that? Okay, let's try 11, and I think we're up here to Iris. Can you read 11, please? Okay, 3 different kinds of symmetry we're going to talk about today. You can have a graph which is symmetric about the y-axis. For example, this thing that looks like a V. You guys see what I mean when I talk about symmetry about the y-axis? Like it's a mirror image. That's right. Everybody buy that? Okay, so that's absolute value of x. I don't know if you're familiar with that graph, but that's what it is. And then here's a graph symmetric about the x-axis. Same kind of idea, but now flipping it over the x-axis, it's a mirror image. And then symmetry about the origin is the tougher one to see. Yeah, so we'll talk about this one in a couple of ways. So first way is if you just pick a random point out here, let's say this point right here. If you decide you're going to walk to the origin from that point, always walk to the origin. So I walk there, but then I decide I've had such a wonderful walk, I'm going to keep walking the same distance in the same direction. So I'm just going to copy that arrow and I land here. Yes? If no matter where you start your walk, you land on another point on the curve, it's symmetric about the origin. I'll draw in a different color. If instead I had decided to start up here, I can walk to the origin, and then I can continue walking that same distance. And if I make a circle real big, I find a point that's kind of the corresponding one. You guys see it? And it doesn't always have to be walking that direction. For example, this picture right here, if you walk from here to the origin, and then you keep walking the same distance, you land on that other point. So both of those graphs, symmetric about the origin. Another way to think of it is what Iris had said. Iris, what did you say? Yeah. So if you imagine, so the picture's getting kind of crowded here. Let me erase some of this stuff. So if you imagine taking this graph and folding it along the x-axis, you guys buy that flipping this top part over will land it down here, flipping the top over, and then flip the bottom part over the x-axis, it'll go up there. And now take that one and flip it over the y-axis. So where will this right-hand part go? If I flip over the y-axis, it lands over there. You buy that? And then you flip the top part over the y-axis, and it's going to do that, which is exactly what it was doing in the beginning. So this is another way to think about symmetry over the origin. If you flip it over both axes, you get right back where you started. Here's a third way to think about symmetry of the origin. Can you guys take your piece of paper right now and just flip it upside down, 180 degrees? What do you notice about that graph? Tyler, what do we notice? Oh, and I like the enthusiasm, same enthusiasm you showed the first time. It's exactly the same when you flip it over. Were the other two graphs the same when you flip them over? No, the V is now pointing down, that's different. What about the other one? That looks the same when you flip it over, doesn't it? No, it's facing the wrong way. This middle guy is currently opening to the right, but I flip it over, it opens left. It's different. It's not the same. But the last graph is exactly the same. And this kind of symmetry actually is something that you might see outside of math class. Have you seen this movie? Princess Bride? Classic. Check it out. But there's something going on here. So let me click on this picture. So I'm just going to flip this guy over because there's kind of two stories, right? There's like the kind of like the real life story at the top, and then there's like this fantasy story here in the bottom. You know, there's pirate ships and like different characters and stuff. But there's some kind of symmetry. What does it say? Right? It says The Princess Bride, right? Did you notice what happened? What does it say?
Wow, that's ingenious.
Yeah. So what kind of symmetry does this guy have? If I imagine drawing my axes, this isn't probably what they were thinking of when they created this video, but that's what I thought of. If I draw my axes, what kind of symmetry does it have? It's about the x-axis. It's about the origin. If you flip this guy over, rotate it 180 degrees, I should say that, don't say flip it over. If you rotate this 180 degrees, it looks the same. That's symmetry over the origin. And for example, you can find this point right up here. And what does it correspond to? If you take your walk to the origin and then you keep going, it corresponds to that point down there. That is symmetric about the origin. Joe, you said there's a name for this thing? That's it. So if you Google ambigram, you will find lots of things like this. In fact, you might even find an ambigram generator where you can type your name in and it will show you what your name would look like if you were able to rotate it and it still says your name. Ambigrams actually played a pretty big role in the prequel to the Da Vinci Code. What was it called? Angels and Demons, I think. Anybody read that one? So anybody know what I'm talking about with this thing where it was like the same? Yeah, like there was this whole fire and earth and all these things that if you rotated the book, my God, it looks the same. These are ambigrams. Okay, so let's come back here and see if we can make a leap from the geometry, like we've got this nice visual stuff happening, and I think we're all on board with that, to the algebra. This is the part where it's going to be tricky for some of us. The algebra here can be quite difficult. Let's take a look at the first picture. I'm just going to pick some point out here. Let's say this is the point that I'm talking about. This is the point 3 and 3. Yes? And then I'm going to pick the mirror image point. What are the coordinates of this? -3 or 3. Agree? What was the relationship between the x's that I picked? Were they the same? They're opposites, right? They're negatives. It used to be 3 for the x, and I picked -3. I have to do that if I've got this symmetry, don't I? If you go into 3, you better go to -3. Those are the points that match up with each other. So we had opposite x's. What was true about the y's? The y's stayed the same. And isn't that what makes it symmetric? Is that you have the opposite x's, but exactly the same y, and that's why it's a mirror image. Okay, let's go to Eric for this first sentence. Thus? Okay, we had opposite x's, x. Say this guy right over here is x, and this guy right over here is -x. And then what was true about the y's? That was unchanged, right? Same y for both. Opposite x's, but unchanged y. What do you think is going on here? Which ones need to be opposite for these 2 points? The x's or the y's? Here it's the y. So if this is some number up here y, then what's the corresponding one down here? -y. And if this is some number x, what's the one down here? Is it x or is it -x? It's x. It's the same. That's how we have symmetry over the x-axis. Matt, can you read the second one? Mm-hmm. That's it. That's what we see. Y became -y, but the x's stayed exactly the same. The x's were unchanged. Okay, and then we go to the last one, the toughest one. So suppose that we have some point up here, x and y, and we're looking for another point. Maybe I can erase this blue thing. We don't want that to get in the way. If there's a point up there, x and y, then there should be some point down here. Is it the same x or is it the opposite x? It's the opposite, because the old x that I had was a positive, and now it's a negative x. Is it the same y or is it the opposite y? It's the opposite y. Andy, can you read the last one? That's right. So we change both x and y into the negatives, and you see what happens to the equation. Okay, so how can I test you on something like this? Let's take a look at the next page. Number 12, we're back here to Taylor. Okay, let's give this a shot. So we don't have a picture in front of us, but even if we did, suppose I just showed you this picture in the middle. Can you look at this picture and know that it's symmetric over the x-axis just by looking at the picture? You can tell it's perfect. It looks like it might be symmetric. It's compelling. But can I know that it's exactly perfect? Maybe the one up above, maybe this point, yeah, like maybe this one here is 4 and 2, and maybe this one down here, it turns out is 4 and negative 1.99. Can you know that it's exactly 2? I mean, you can't, right? Just by looking at it, you can't know that it's perfect. And Iris makes another good point. I'm only showing you a small part of the graph, but maybe the graph down here does what you expect, but then the graph over here does not do what you expect. Is it symmetric with respect to the x-axis? No. So you can't look at a graph. You can't look at a graph and just know that it's symmetric or not. The only way to actually show that something's symmetric is to do algebra, which we're about to do. So here's what we're going to do. Your choices are replace x and y with x and negative y. That's one choice. Replace x and y with x and negative y. Another choice is to make x, y. I'll list your 3 choices here. You could replace it with that, or finally with that. One of these 3 things is supposed to show us symmetry. So I'm gonna walk through these ones real quick here. Now I'm gonna pick the right one, and then we'll pick the wrong one. So let's pick the right one first. The right one here is to replace x and y with x and negative y. So I used to have x. What do I have now? Still x, right? X is still x. So this x is still x. Equals. Yeah, so that y becomes negative y. So we've got negative y, but it's in parentheses to the 4th. The y got replaced with negative y, minus, and then what happened to this y? It's also negative y. So you physically change all the y's into negative y's, which might mean you need to bring in parentheses. So far, so good? Now we need to use some logic. If you raise something to the 4th power, what happens to a negative? It becomes positive, right? If you have negatives and you raise them to the 4th power, they become positives. So do you guys believe that negative y to the 4th is exactly the same as positive y to the 4th? Because all those negatives go away. Then there's a subtraction. How about that negative y squared? What is it the same as? It's the same as y squared. And then I'm just copying the x straight down. And then we look at this and compare it to what we started with. What do we see? It's the same thing. And that's what we're after. We have just proven that this equation has a certain kind of symmetry. Which symmetry was it? You can look at your list and put it on the reference card for the quiz. xy became x negative y. What kind of symmetry is that? So this is symmetric about the x-axis. Questions on that? I said I was going to pick the right one. This was the right one because the equation ended up coming right back to where it started. So what happens if you pick the wrong one? Suppose that instead we had done this. What does x become? Negative x. What does y become? Stays as y. So if I just replace this x with the negative x, I'm going to write this and then I'm going to erase it. That becomes negative x equals, and then the y's stay the same, right? Is that equation the same as the one we started with? It's just different. It's no longer x equals y to the fourth minus y squared. That is not the same equation. And there's no algebra I can do to make it the same equation. What does that mean? It means that wasn't the right substitution. And that was the y-axis symmetry one. It doesn't have y-axis symmetry. That's our conclusion. Okay, let's try the next one. I've got an x squared, and I've got an absolute value of x. It feels like you could change those x's into what, and it'll still be the same. You could change those x's into negative x's, because you got an x squared, and we know that negatives disappear when you square them, and you've got an absolute value. And what happens to negatives when they're in an absolute value? They disappear as well. So it feels like replacing x with negative x is a good idea. If you replace y with negative y, will it stay the same as it is now? No, it's going to change. It will fundamentally change to negative y, and it'll just be different. So it seems like this is a good choice. So let's try. Instead of x, what are we putting? Negative x. So I've got negative x squared plus, instead of that x, negative x. And what was y being replaced by? Was y, it just stays as a y. Okay. Negative x squared is the same thing as x squared. Absolute value of negative x is the same as absolute value of, oops, x. And what do we observe? They're the same. And then the conclusion, once we see that they're the same, well, let's see, that was the one where x became negative x. This is symmetry about what? About the y-axis. Let's have a look at part C. Okay, so in the first example, we replaced y with negative y. In the second example, we replaced x with negative x. If you guys were interested in taking a wager, which one would you guess? We're going to try on the last one. We're going to do both, negative x and negative y. And it's okay if it's not obvious that that's a good thing to do just looking at the equation. It becomes easier with practice, but even if you go wrong, I think we've seen what it's supposed to look like. It just won't turn into the original equation if you pick the wrong one, so pick a different one. So let's try this one. X becomes negative x, y becomes negative y. This x becomes negative x. It is still squared. That y becomes negative y. It is squared. Plus x becomes negative x. Y becomes negative y. 1 becomes 1. No reason to change that. Negative x squared is the same as x squared. Negative y squared is the same as y squared. Here's where the funny thing comes in. Maybe it would have been hard to predict, but what happens here? Negative x times negative y is positive xy. Still equal to 1. And how does that equation relate to the top one? They're the same. So what kind of symmetry does this one have? This is symmetrical over the origin. I'm always curious about what these things look like. Unfortunately, you cannot type. We're gonna graph stuff on the calculator next class, and unfortunately, you can't graph this x squared y squared stuff on the calculator. But there are free things out there that you can graph them on. So I think I have like 15 seconds. and we're going to graph this thing on GeoGebra in 15 seconds. So here it is, x squared, y squared, x to the second. Actually, it might not work. I hope this isn't a build up for nothing. We'll pause the video just in case.